Chapter 5, Trigonometric Identities. So in 5.1, as we saw briefly a minute ago, we're going to look at 6 sections in chapter 5. And the first one about trigonometric identities in 5.1 has us look at the fundamental identities, sort of the most important ones that we used most frequently, and how to use them. And so fundamental identities are basically the ways that we sort of defined our primary trigonometric functions, so that cotangent is the reciprocal of tangent, secant is the reciprocal of cosine, tangent is equal to sine divided by cosine, cotangent is the reciprocal of that, things like that. So we're going to want to make use of these facts to do some problems. And we've been using these facts already to some extent. But the fundamental identities that we've thought of before and haven't used that much are that the sine squared theta plus cosine squared theta is equal to 1. And tan squared theta plus 1 is equal to secant squared theta. 1 plus cotan squared theta is equal to cosecant squared theta. And then there's some even and odd identities. We looked at some of these when we were looking at the functions themselves. When we define them, we sort of recognize these things a little bit. We just looked at these as properties of the graphs of sine and cosine and the rest of the trig functions. But now we're looking at them as ways to make symbol manipulations or to adjust things in an equation as an identity. So for example, when they show you this first even odd identity here, basically all of the identities in this box are some sort of an equation that says that one thing is equal to another. So the idea when you have an identity like this is if you have either the left side of this equation or the right side of this equation occur in some expression or in some bigger equation, then you can replace one of these with the other. So the idea that you want to look at when you see this is that something like sine of minus theta can be replaced by minus sine theta, or vice versa. So the way these identities are going to be used is they're saying, since these two things are always equal to each other, if it helps you to do a problem, you can always replace either one of them with the other. Or in the case of something like one of these primary identities, where you have sine squared plus cosine squared equals 1 for any given angle theta. When you have two trig functions in an equation, that means that if you know the value of one of those two, then you can plug that in and solve for the value of the other. So the way these top identities are used is if you know sine theta or cosine theta, you can solve for the other. So I'm pointing this out. We will see this done in problems. We will look at examples where they do this. But right away, trying to understand what this little box of identities, of these fundamental identities, are trying to give to us, what the purpose of these things are, helps us right away. So as we're learning to use these to do problems, we can see why these work and how they help us do problems, why they work to help us solve problems. So let's take a look at where they begin here. So first they have a note: in trigonometric identities, theta can be an angle in degrees, a real number like a radian measurement, or a variable where you just don't know what it is, as long as it stays the same value everywhere you see the same variable. But they're saying it could be degrees, could be radians. So here's an example, example 1. So let's change this here. So if tan theta is equal to -3/5 and theta is in quadrant 2, so this is one bit of information we're given, and this is a second bit of information we're given. Then find each of the function values below. And of course, the slides are a little messed up. I think this is just supposed to be secant theta, or the theta got put too low for some reason. So what happened here is they told us the value of tangent, and they asked us to find the value of secant. They told us the value of tangent, and they asked us to find the value of secant. So if I go back to that first box, let's think about how what they showed us in the first box helps us achieve this goal. We were told tangent, we want secant. So as I was saying with sine and cosine in the Pythagorean identities, if you know sine or cosine, you can solve for the other. So in the problem we just looked at, they told us tangent and they asked for secant. So notice this second Pythagorean identity here. In this one, this is an equation involving tangent and secant. So just like the sine and the cosine one, if you are told tangent or secant, you can solve for the other one. So in the problem we just looked at, they told us tangent and they asked us to find secant. So that's why we would use that trigonometric identity, because we can plug in for the tangent value and then solve for the secant value. And so that's the idea of what they're trying to demonstrate in this first example. We were told tangent and we're asked to find secant. So we choose that identity that I just was highlighting, because then we can take the value of the tangent and plug it in for tangent and then solve for secant. Because that's our goal, to find secant theta. All right, now let's see how they did that. So then what they do is they plug the tangent value that they gave us in for tangent, replacing it where it's supposed to be squared. So tan theta squared, since tan theta is -5/3, becomes -5/3 squared. And they leave the rest of the identity alone. And so then after you square 5/3 and add it to 1, combining doing the arithmetic on the left side, you get that secant theta squared is 34/9. So then to solve that, you would square root both sides, because you're trying to solve for secant theta. That's our goal. And it's squared, so we need to get rid of the square. So I square root both sides. And when you square root both sides, you need to do a plus or minus on the square root. So they didn't put this in good detail here, but what I'm going to point out then is what this then means is that secant theta is equal to either the positive or the negative square root of 34/9. And when you have a square root on a fraction, you can apply it to the top and the bottom. So that means the positive or negative square root of 34 divided by the square root of 9, which is 3. So at this point, there would be two possible values for secant theta that would work when tan theta is -5/3. But the second bit of information they told us that we now want to lean on is that theta is in quadrant 2. And so in quadrant 2, and you could sort of imagine this again, here's our graphing system. Quadrant 1 is in the upper right. Quadrant 2 is over here on the upper left. So if we're in quadrant 2, what would be the sign of secant? Well, we can remember that secant is 1 over cosine theta. And then in cosine is the x value of the angle theta point. So in the second quadrant, the x value is negative and the y value is positive. So that means that in quadrant 2, cosine theta is negative. And so therefore secant 1 over cosine is negative. And so as they then say, in quadrant 2, secant theta is negative, which I just tried to explain. And so they choose the negative of that plus or minus square root. And so they end up saying that secant theta has to be negative square root of 34 over 3. So they put several things together here, but we used a trig identity. And since they gave us tangent and asked for secant, we used the identity that put tangent and secant into the same equation so that we could solve. So then it says for part B, so we still have that tangent is negative 5 over 3. And we still have that theta is in quadrant 2. In part B, we're told to find sine of theta. Well, what we know is that tan of theta relates to sine because it's equal to sine over cosine. And so if we're trying to find out what sine is, we can take this expression and solve it for sine by multiplying by cosine theta on both sides. Because over here, the cosine thetas would cancel. And then you're left with sine theta is equal to cosine theta times tangent. Again, we were told what tangent is. Then in part A, we found out what secant was. And secant is the flip or the reciprocal of cosine. So we can use it to find out what cosine is. So they're showing here, secant is the flip of cosine. So cosine is the flip of secant. And we know what the tangent is because that was given. And we know what the secant is because we figured that out in part A. So if we substitute those in, we get an expression. And then we would simplify that expression to get an answer. Now let's take a look at how they did that. Let's look at the simplification. And they had 1 over the square root of 34 over 3 with a minus times minus 5 over 3. So that's what we had to simplify. Well, first of all, a negative times a negative is a positive, so these negatives cancel. And when you flip root 34 over 3, you get 3 over root 34, which is multiplied, that's a positive, not an addition problem, multiplied by 5 over 3. And then when you multiply 3 over root 34 by 5 over 3, the 3's cancel, and that's how they ended up with this. And then they rationalized the denominator to get their final answer for sine. So in this part B, we had to use the answer that we got from part A in order to replace secant theta with that value. But nonetheless, we could do parts A and B all by being told what tangent was and what angle theta was in. I'm sorry, which quadrant theta was in. So again, just to highlight what's going on here, we don't really have graphs to look at other than maybe just considering quadrants of the graphing system. There's lots of algebraic manipulation here, taking an equation, substituting, multiplying both sides to clear things, simplifying. So there's lots of algebra work in chapter 5. So finally, they say, well, what is cotangent of minus theta? So the first thing they remind us or use, since we are told what tangent of theta is we'd like to express cotangent in terms of tangent. And cotangent is the flip of tangent. So they begin with the reciprocal identity and just replace cotangent of minus theta with 1 over tangent of minus theta. Going up to the original box here. So they were using cotangent is 1 over tangent. And then also we know by the even and odd properties that if you have tan of an opposite of an angle, you can replace that by minus tangent of the angle. And so in the problem we were just looking at, they use the negative angle identity. So instead of doing tan of minus theta, they make that as minus tangent of theta. And tangent of theta is given to us in the problem as negative 5/3. So they replace tangent of theta with minus 5/3 and simplify to get the answer. And so they ended up starting with this and getting all the way down as this for the answer for that. All right, let's see if they do another one of these for us. We have a caution. To avoid a common error, when taking the square root, be sure to choose the sign based on the quadrant of theta and the function being considered. So we saw that in the example up here. So the caution is about what I was showing here, that if they tell you what quadrant theta is in, then you can use that to see what the signs of x and y would be in that quadrant, and then that will tell you, based on sine or cosine or one of the other functions, what sign you should have for your answer. So that's a caution they have, cautionary box there. All right, so let's see, example 2. So this one is more challenging because they're not giving us an equation to solve. The task, which is a little bit misaligned on this slide here, but the task is to write cosine x in terms of tangent of x. So what does that mean? When they say to write one function in terms of another, that means you want to write cosine x is equal, and then you want to have some expression that has only tan x as a trig function in it. So the basic idea to do that is to try to get an equation that has tangent in it and cosine in it, and then solve it for cosine. Isolate the cosine and shove everything else to the other side so that you have an expression on the other side that has a tangent or a couple of tangents in it somewhere, but nothing else. Well, we have an equation with tangent in it that relates that to secant from our identities. And we know secant is 1 over cosine. So if I replace secant with the 1 over cosine in some way, then that will make it so that I have an equation with cosine and tangent in it, and then I can solve that for cosine. So that would be the idea of what they're now doing in front of us, because they're going to show you steps to do the example problems that they're demonstrating. But the hard part is when you're looking at what they did is initially you have to see what did they do there, but the harder part is to realize why did they do that? And so that's what I'm trying to describe, the motivation here. If the goal is to write cosine x in terms of sine x, that means that you want to get cosine x equals to something with tan x in it. And that means you want to have an equation that has cosine and tan where you can then isolate the cosine in that equation. Since we have an equation already with tan and secant is the flip of cosine, that's how we get those two in the same equation. That's the idea. So they start by saying, all right, well, if we have 1 plus tan squared x is secant squared x, since secant squared x is the flip of cosine, I can flip it to get cosine. So they take the reciprocals of both sides of the equation. They flip both sides, because when you have 1 over secant squared, that becomes cosine squared. So using the reciprocal identity that the reciprocal of cosine is secant and vice versa, 1 over secant squared becomes cosine. And now what I want to point out is that here was their initial goal. Now you have an equation with tan and cosine. And so now if you solve that for cosine, that's what they were asking for at the outset of the problem. So the way they solved this for cosine was because cosine was squared, they square rooted both sides. So in the next step, they took a square root of both sides and they used the plus or minus, because there's nothing here saying which quadrant the tan would be in or anything like that. We're just solving for cosine. We don't know if the cosine sign would come out to be positive or negative. And so then they get this root with the plus or minus, which they simplify a little bit by applying the root to the top. The square root of 1 is 1, and leaving the root on the bottom. And then they rationalize the denominator, and the symbols got a little bit messed up here in the slide, as is normal the case. And that's just supposed to say tangent 1 plus, all right. Anyway, so before they rationalize the denominator, there's the answer. And then they multiply the top and the bottom by the radical on the bottom. So this is an example where you're not actually getting a number for something. You're not solving and getting a value. You're just rewriting an equation in terms of one of the things in the equation. And that's some pretty high level algebra. So students may be kind of uncomfortable with examples like example 2 here, just depending on how comfortable you are with your past algebra. That may take some refreshing. All right, well, let's progress a little bit. There's only a couple slides left before we're going to switch over and try to do some homework problems for you, or some practice problems. So here's another kind of problem where you're using trig identities. Again, it's not written very well, so I'm going to have to adjust this a little bit. So this is 1 plus cotangent squared q and 1 minus cosecant squared q on the bottom. So they give you this fractional expression here, and they want you to write this in terms of sine and cosine. So anytime they ask you to write something in terms of sine and cosine, it means you just want to replace any of the other 4 trig functions, tangent, cotangent, secant, cosecant, any of those with their definitions with sine and cosine. And basically that's that tangent is sine over cosine, secant is 1 over cosine, cosecant is 1 over sine, those things. And then of course you'll need to simplify whatever's left. So unfortunately the notation is still not real friendly here, but again, they started with 1 plus cotangent squared q on the top and 1 minus cosecant squared q on the bottom. And so to write in terms of sine and cosine, you want to replace cotangent with cosine over sine. So because of that, cotangent here, which is squared, becomes cosine over sine squared, and they squared both of these. So they did a little bit of extra work in here. So this means cotangent of q squared, and that would be cosine q over sine q is squared. And if I square a fraction, then I square the top and the bottom, and that's how they ended up with what they have there. Similarly, cosecant is the same as 1 over sine. And so if cosecant is squared, that's the same as 1 over sine squared. And so in this first step that they did a little bit too quickly and left out some of the ideas behind it, but that's why I'm here to fill that in. In that first step, they converted the expression, so now it is only in terms of sine and cosine as requested. So we now have written it in terms of sine and cosine, but we then have to simplify, the expression so that no quotients appear. So we have to get rid of these fractions in here. And this is really kind of illegible here, so let's not pay attention to that. It's just the slides are so bad here. So how is it that I would then take this expression that we have here, and how would I get rid of the quotients? We have specifically these little fractions inside of the big fraction. Well, when you have little fractions with these denominators of sine squared q in them, you multiply the top and the bottom of the big fraction by the denominator's LCD of the little fractions, which in this case is sine squared on top and the bottom. Again, this is a tactic taught in algebra that might have been forgotten at this point. So I need to multiply the top by sine squared q, and I need to multiply the bottom by sine squared q. When I do that, you'll see that we have to distribute the sine squared to both the fraction on the left and also to the one on the right. So that would lead me on the top to having, let's change colors, having sine squared q, because sine squared times 1 is sine squared, plus, and when the sine squared multiplies by the fraction, the sine squareds cancel, leaving cosine squared q. Then similarly on the bottom, I'm distributing the sine squared to the fraction on the right and also to the 1 on the left. Sine squared times 1 is again sine squared q. This time they're separated by a minus, and sine squared q times 1 over sine squared 2 would just give you 1. Darn algebra. All right, so moving on to, I think that's what they're saying we should have left here. So let me transfer that down here. So at this point, what they have is, and what we have is sine squared q plus cosine squared q in the top, and sine squared q minus 1 on the bottom. So now, how do we simplify this? Well, you might be tempted to do this. I'm going to do something you're not supposed to do just in case you're tempted to show it looks attractive. If you're trying to simplify this, you might be tempted to cancel out the sine squareds. But you can only do that if they are factors, if they're multiplied in the top and the bottom. Because they're separated by addition and subtraction in the top and the bottom, that would actually be wrong. We can't do that. So instead, we want to recognize that our first identity on the box that we looked at in the beginning was that sine squared plus cosine squared is all equal to 1. So that means I can replace all of that in the top with a 1. And similarly, if sine squared plus cosine squared equals 1, then if I subtract 1 from both sides and subtract cosine squared from both sides, I'm left with sine squared minus 1 is equal to minus cosine squared. And I'm pointing that out because what they're doing is they're also replacing the bottom with minus cosine squared q. And that leads them to this fraction here. So they didn't really show that. They just referred to the identities that are being used, the Pythagorean identities. But that's what they did. So they used these identities to replace sine squared plus cosine squared in the top with a 1. And they used the identity rewritten a little bit to replace sine squared minus 1 with minus cosine squared in the bottom. And that's how they get to this step here. Now they did say to simplify without having any quotients, and we still have a fraction left here. So we would want to recognize that 1 over cosine squared is secant squared. And that's hard to see. There's a little minus there. So in this step, they use the reciprocal identity that 1 over cosine q is equal to secant q. I said q and wrote squared, ahead of myself. Secant of q. And therefore, if the cosine is squared, then the secant is squared. And if there's a minus out front, then there's a minus out front. And so they replace the whole thing with minus secant squared q. And at this point, we've simplified all the way down so that there are no quotients left. Now, it started by saying rewriting in terms of sine and cosine, but that's not where they finished. So why didn't they leave it in terms of cosine? Like they could have left it in terms of cosine instead of converting to secant. What they're trying to show here is that one of the ways to simplify an expression, one of the ways to accomplish that is to convert everything in terms of sines and cosines and then algebraically see how it simplifies so that you can get the simplest possible answer in the end. So in this final caution, it says, when working with trigonometric expressions and identities, be sure to write the argument of the function. Don't forget to write the theta or the q or the x. For example, we would not write sine squared plus cosine squared equals 1 without putting the theta. There should be a theta here and a theta here, or an x or a q or something like that. And that's it. So that's how they finish. So this last example, let's just take one overview of this again, see if there are any questions. So it says to rewrite the expression in terms of sine and cosine, then simplify the expression so that no quotients appear. So we started by replacing all non-sine cosine trig functions in terms of sine and cosine. That left us with a big, ugly, complex fraction. So then we used algebra tactics to simplify the fraction by clearing out the little small denominators in the little fractions first. Then we used more trig identities to simplify the fraction that remained. And then in the very end, the final fraction could be eliminated by using a reciprocal identity and getting it all just to be negative secant squared q. And so in the end, what that means is that this initial thing they gave of 1 plus cotangent squared q divided by 1 minus cosecant squared q, that whole thing ends up just becoming equivalent to negative secant squared q. So that's a pretty drastic simplification from what they started, and they did it by converting everything into sines and cosines in order to simplify algebraically, and then going back to the simplest trig function they could. So their third example is pretty involved. Are there any questions, comments, discussions about any part of this third example? Anything I should explain better or elaborate on to help you understand it?
Do I have to know about these words like quotient identities and like Pythagoreans, like something at the below pages? Yeah,
I mean, all these labels on the side that they say quotient identities, that kind of stuff.
Yeah, and the distributive property, Pythagorean identities, reciprocal identities.
Only as they show up in the problems, because keep in mind, what is it that you're going to be tasked to do? What is it that we're going to see if you know? You're going to be given problems to do in my math lab.
Yeah.
And unless they ask you what is the distributive property, what is a Pythagorean identity, unless they ask you that, then they're just using the labels here to help you identify what they were doing. But what's really the goal is to get the answer in the end. Like if this were a problem on my math lab, all they're going to want is the minus secant squared q at the end, right? They're just going to want the answer, right?
Yeah.
And so you have homework problems where you practice this, then you have quiz and chapter test assignments, and then you have a midterm. But all of those problems are on my math lab, in which they, in the end, ask you the answer. So as you're doing the problems in my math lab, you're getting a way to see what the expectations of you are. So I honestly don't know if they have some problem that somehow asks you to label one of the identities or something, but I don't recall seeing that. And we're about to do a few problems now for practice as well. So certainly if you come across that, then take note of it, see what they asked for you. But I think you would just more normally expect that they're just going to want the answer. And the reason they're labeling these is so that you can go back to this box at the beginning. If you're like, how did they do that? Well, you can go back here and see what they used. Oh, they used one of these Pythagorean identities or something like that. They used one of these quotient identities or one of these reciprocal identities. They just have labels so that they can try to talk about what they did, so that if you don't know what they did, you can figure it out.
Uh-huh.
Does that make sense?
Okay.
Yeah, I don't think it'll be very vocabulary focused. So here are practice problems for the first section of chapter 5. So maybe there's 38 of them again, but these are just the practice ones. These don't count toward your grade, but let's see if we could start doing some of these. Maybe grab number 5 here and see what it says. So really simple statement of the problem. They give you cotangent of theta and which quadrant theta is in. And they ask you to find out what sine of theta would be. So it doesn't look like they at any time ask us which identities we used or anything like that. They just want you to feel that you could get the answer. But we kind of know that the way we do that has to somehow involve those identities and things like that. So the way I remember these is one of the trig identities, cotangent is to cosecant. There we go. Yeah,
I think then cotangent, like each square the cotangent and minus 4/9 and plus 1, and make it to the cosecant square.
Nice. So here's the identity he's referring to. So let me bring it up. And here's why you might look it up. It's 1 plus cotangent, and I apologize for the slow, sloppy writing, theta squared is equal to cosecant squared theta. This is one of our Pythagorean identities. So how does this help us? It allows us to convert cotangent into cosecant. When you have an equation with these two things in it, you can solve for one by plugging in the one that you know. So we would be able to find the value of cosecant because we are told the value of cotangent. And cosecant, we remember, is 1 over sine. So cosecant squared would be 1 over sine squared, and we're supposed to find sine. So in this case, I don't think this will help us, even though we could use it, but we don't need to. So from the Pythagorean theorem, one of these identities, we can go from cotangent to cosecant. Cosecant, by the reciprocal identities, is the flip of sine, and they've asked us for sine. So that's the pathway to how to get to this answer. We would then have to know which quadrant it is to choose whether it's a positive or negative value for sine, but that would be the path that we would take. So let me pause there and see if that makes sense. I can continue in the problem in a second, but the idea is this is the pathway to get the answer that they're asking for. Okay, so I would, in place of cotangent, I would put -4/9, because we're told that value. And then, of course, that's squared because the cotangent is squared. So that gives me 1 plus, and 4/9 squared, -4/9 squared is 16 over 81. And that's equal to cosecant squared. Oh, sorry for the writing. That's why I usually switch to my tablet, because it's so much harder to write on the mouse on here. All right, so if I add 1 to 16 over 81, then that's 81 over 81 plus 16 over 81 is 97 over 81. And that's equal to cosecant squared, which is 1 over sine squared theta. So now I want this in terms of sine. So I would flip both sides because I've got sine in the bottom and I don't want that. So I would flip both sides, and that would give me that sine squared is equal to the flip of 97 over 81. So that becomes 81 over 97. And then I'm trying to solve for sine, so I would square root both sides. And when you square root both sides, you want to remember that it could be a positive or a negative answer. So that would give me that sine has to be the positive or the negative square root of 81 over 97. The square root of 81 is 9 over the square root of 97. So now I need to choose between the positive or the negative, and I need to rationalize the denominator. Well, since theta is in quadrant 4, in quadrant 4, sine of points in quadrant 4, which is the y value, is negative. So since the sine of an angle in quadrant 4 is negative, I'm going to choose the negative root here. And to rationalize the denominator, I'm going to multiply. Doesn't say to do that. I wonder if it would take it without it. Well, let's say I do it here, and then we'll see if it'll take it without it, if it doesn't specify. I'm still trying to figure out if the problems always want you to rationalize a denominator or not. So if I rationalize the denominator, I would just get 97 in the bottom and 9 times root 97 in the top, and I would choose the negative answer for the sine. So let's see. I'm going to try it without it first. So I'm going to put -9 divided by the square root of 97. And let's see if it lets me leave the root in the bottom. It did. So we didn't even need to rationalize the denominator. I did need to put something equivalent to -9 over square root of 97.